All right, so we are going to look at logarithmic functions today through the lens of exponential functions. So last class we talked about exponential functions for a little while, graphing them specifically, and we're going to look at graphing log functions on this video, keeping in mind what we talked about last time with the exponential functions. So first of all, just remember, always be ready for those entry tickets. It could be on the video you're watching now. It could be on the stuff from last class. But be ready when you come in to take one of those quizzes based on what you've learned in the past. So you should always be brushing up on your skills. Make sure you're understanding what you have been working on. All right, so we're going to talk about logs today. So logs are an inverse of an exponential function. So the log or the inverse functions we're familiar with. X squared, to undo the x squared, we take the square root. Those are inverses. To undo the sine of x, we take the inverse sine of x. Those functions undo each other. And that's all a log function does. It allows us to, it allows us really to algebraically solve for y. So if we think back to what our inverses are, we switch the x and the y around, and then we rewrite it in order to get the y by itself. So, in the previous examples we've done, it was easy. It was like a linear function or, a square root function, and we just had to get the y by itself by squaring or by doing the inverse sign or by doing some division to undo the multiplication. Here, there's no way to get the y by itself unless we rewrite this function in log form. So to go from x equals 3 to the y power to rewrite this with a y equals, we need to use the log. So it becomes y equals log base 3 of x. So this is what we need to get really good at the next couple of classes, being able to switch back and forth between exponential and logarithmic form. Okay, so notice kind of the big thing that always helped me remember, and I'll give you a couple other strategies in a minute, but the exponent, whatever that exponent is, it's always the output of the log function. And I'm going to write that down for you in a minute. So here's how some of my past teachers helped me remember how to go back and forth. So log base b of x equals y. The base of the log is the base of the exponent. So the base ends up in the same spot. It's like the lower part of each function, of each function. And like I mentioned, the exponent, the power, is the output of the log function. So if you are in log form and you want to write it in exponential form, we start here with a low part a b to the y power equals x. So kind of going around in a circle. That's how my teacher helped me remember it back when I was in your shoes. So b to the y equals x. And that's how I showed up, how I arrived at that next, the next function down below there. Okay, so let's graph. All right, so that's what I mentioned a second ago for log functions. The exponent is the output of the function. So let's fill in for a second. I'll graph as you guys graph. This is what we spent a lot of time on last time. Let's sketch the graph of y equals 2 to the x. Actually, I'm going to pause while you guys do this. And then I want you to fill in this part of our table right here. So the domain, range, x-intercepts, y-intercept, and where the asymptote is. So I'm going to pause while you do that. And then when you unpause, it will be done for you. So pause now. Okay, so there is that. You didn't need to plot those points. I did just to help us kind of think about what we're going to do with this log function in a second. But there's our y equals 2 to the x. Our asymptote is at y equals 0 because it can never get below that line. So we talked about that, a lot last class. So our log function is when we switch the x's with the y's. So x comma y, all those ordered pairs become y comma x. So I could just go through those pairs I plotted and just switch the coordinates around. The other thing we talked about when we're graphing this is this is a reflection over the line y equals x. So if I wanted to look at this graphically, I could draw on the line y equals x and I could visualize this reflection. So my log function, kind of the home base point that we're always going to be able to plot, just like we can plot 0, 1 for the exponential function, we can always plot the point 1, 0 on a log function. All right. And then we know the point 1, 2 is on my exponential. So the point 2, comma 1 is on my log function. 2, 4 becomes 4, 2. 3, 8 becomes 8, comma 3. And the same thing happens here. Negative 1, comma 1/2 becomes 1/2 negative 1. And just like that exponential function gets closer and closer and closer to the y-axis, the x-axis, this log function gets closer and closer and closer to the y-axis. So there's what this exponential function looks like. And it's going to gradually, slowly go up that way forever and ever and ever. And our asymptote, our vertical asymptote, is right here at the line x equals 0. It can never, ever, ever, ever cross that line. So the x's and the y's are changed, the domains and the ranges are changed. So for a log function, the domain is 0 through infinity. Got ahead of myself. All right, we can never put 0 in. 0 does not work. So I can't take log base 2 of 0. That would be an undefined value. The range is all real numbers. It's going to go down forever and ever and ever, and it's going to go up this way very slowly forever and ever and ever and ever. All right. My x-intercept of the parent function is always going to be 1, comma 0. So that tells me anytime I put 1 into a log function, so log base anything, log base 8 of 1 is always going to give me 0 as an output. All right. There is no y-intercept unless there's transformations happening. But on the parent function, there is no y-intercept, and the asymptote is at x equals 0. So that's kind of the nuts and bolts, everything we want to know about graphing log functions. A really nice rule of thumb, let me label this for you. This is, I'll just write y equals log base 2 of x. So they always go through the point 1, 0. The next point right here that we can plot easily always comes from the base here. So this point would be 2, comma 1. All right, if it was log base 7 of x, we would plot that point at 7, comma 1. All right, but we're going to look at that in a minute. So there's our log function. That's the parent function of log base 2 of x. All right, the next thing at the bottom of your screen, this should have been nudged down a little bit so you can write it and then flip. But the natural log function is used when the base of a logarithm is e. So, we just did log base 2. If it was just log of x, I didn't mention this, but we're always going to assume if there's nothing there that it's log base 10. All right, so log of x, we're just going to assume it's log base 10. So e to the x, we mentioned that last class. E is such a special number. It has its own log. It has its own it has its own function, exponential function. It also has its own logarithmic function. So y equals e to the x. We switch the x and the y around. We rewrite it in log form. So log base e of x equals y. You're never going to see it written like this. You'll never see log base e. You'll see it written this way. That's all it is. Those are equivalent. Those are the same exact thing. But e is such a commonly used base, it has its own special logarithmic function that goes with it. So the base e, just like base 10 is implied, here the base e is implied. So what I would like you guys to do, just using the skills I just went over, I want you to think about graphing these 3 functions. And I'll do the same thing. I'll graph these while we're paused. I'm going to do the log base 3 of x in red. I'll do log base 2 of x in blue. And then if you want to wait for me to do this one, you can. If you want to try it out on your own. But those are the 3 functions I want you to plot right now. And think carefully what I said on the last page about where that second point is plotted. All right. And then also remember the number e is 2.71 and then a lot of decimals. So keep that in mind as well. That'll help you. All right. So go ahead and start graphing those first 2 now, and then we'll come back and do the third one together. All right. So there's log base 2 of x and log base 3 of x. So log base e of x, since that number e is right between 2 and 3, that's where I'm going to plot it. If you look at my graph, I just plotted that point. There's log base e. There's the point e, comma 1. So when you graph that e function, that log base e, the natural log of x, it slices right between log base 2 of x and log base 3 of x. And the reason is e, the number e, is right between 2 and 3. And that's why we have that, that first point after 1, 0. The second point we plot is e comma 1. All right, so hopefully that makes sense. But now that we know how to do that, we can graph anything just based on the transformation rules that we've done. All right, so the domain for all the log functions is 0 through infinity. The range is negative infinity through positive infinity. The x-intercept for every parent function is going to be 1, 0. That should say y-intercept. There are no y-intercepts. It cannot cross through the y-axis for the parent function unless there's the transformations, which we're going to talk about in a second. It's an increasing function. It's always going up forever and ever and ever. There is an asymptote, a vertical asymptote at x equals 0. And yes, it's continuous because we can draw the whole thing without picking up our pencil. All right. Let's see how we do with our transformations. So we're going to sketch this function. We're going to find the domain, range, and vertical asymptote. And I want you to state the transformations as well. So why don't we do that? So let's think back to our transformation rules, our BHAK. So our B value here in front of the x, there's our B value is a 1. There's our H value. Our A value is also a 1 right in front of the function itself. And then our K value is here. So the transformations on this function, there's no reflection, there's no vertical stretch or horizontal stretch or shrinks, but we are going to shift this graph 1 unit to the right. Remember, order matters. So there's the first step. And the second step, we're going to shift up 3. So I want you guys to pause, try to graph this on your own. So start with the parent function, then just kind of chip away at it, just like we did with our exponential functions last time. And when you unpause, I'll talk you through what I did. All right, so go ahead and pause now. All right, so there's what I have. There's my lightly in yellow dashed line there. There's the function, the natural log of x, so log base e of x. And I have my vertical asymptote as well. So when we do these, we're going to just kind of follow what's happening. We're going to shift 1 unit to the right. So we're going to take all these points, just kind of move them 1 unit to the right. But really important here. So I'm going to, I'll shift the whole function there. But really important, that vertical asymptote comes with us. All right, the domain kind of shifts with it. So now I've shifted everything 1 unit to the right. So the point 1, 0 is now at 2, 0. All right, and the point e comma 1 is now at, I guess, e plus 1 comma 1. So now we can shift everything up 3 units. This is the last step, up 1, 2, 3. So that home base point is now at the point 2 comma 3. And then we can kind of follow along with this e points. It's going to move up to about here. Where am I? Right. So it's going to move over right about here. Yeah. So there's my function after the transformations. And I will do my best to draw a nice graph here. That's pretty good. And it turns right down steeply. And it goes up this way gradually forever and ever. So there's my function. So f of x equals 3 plus the natural log of x minus 1. So a shift over 1 and up 3. All right, so my graph's a little bumpy there. Sometimes it's a little hard to do this on my tablet. But that's what we should roughly have after we've done our transformations. So let's go ahead to the next page. I want you to try this one completely on your own. So just see how you do. And then same thing, when you unpause, I will kind of show you my answer and talk you through it. So be really careful about your first step, finding that B value. All right, so go ahead and pause now and try it out. So here's what I think we're going to do. I realized I forgot to write the domain, range, and asymptote for this first one. So let's do this. So I'm back on the previous page here. So our shift right 1, up 3. So really, really careful here. Our domain, since we shifted 1 unit to the right, changes. Right, our asymptote got brought over 1, and our asymptote, or our domain, is now 1 through infinity, which means the vertical asymptote is now at x equals 1. So everything got shifted 1 unit to the right. All right, and our range is still from negative infinity to positive infinity. All right, so here's what I want you to do. I would like you to try this question out on your own. This will be what I want you to put on your Google form tonight. So I want you to take a picture of this problem. If you prefer to do it through Canva, that's fine. But we will come into class next time and we'll talk about this, how you did and what questions you have. So this is your homework. After watching the video, try graphing this one out on your own. Otherwise, if you have any questions, let me know and I'll see you next time in class.